a different form of that data. So one thing we can do is think of language processors as programs, and like all programs, we think of them in terms of what they take in, what they produce, and how they're implemented. So these T-diagrams are sometimes a useful way of thinking about it, because we're trying to be explicit about, on the left is the source language that's coming in, on the right is the target language that's being produced. The middle part represents the actual code itself, the functionality. But we also want to know, well, this is a program, and programs have to be written in a language. What language is it written in? The T-diagrams try to sort of capture all of these things together. So this addresses the issue of where do compilers actually come from. So Go, for example, language from Google, is an example of a self-hosting compiler, because currently the Go compiler is written in Go. So if you want to compile a Go program, you have to compile a Go compiler, but in order to compile a Go compiler, you need a Go compiler. So these compilers are called self-hosting because they compile themselves. There's always this chicken and egg thing about, well, if C didn't exist and there had to be a first C compiler, how was the first C compiler written? So what usually happens is something called bootstrapping, which is a process of going from the very, very simplest, lowest level languages, which are very difficult for humans to write in, and then repeatedly building higher level things on top. So in this case, on the far right hand side, the very first thing I need is something that is written in machine language, because that's the only thing I have, produces machine language, but accepts something very slightly higher level. So assembly is much easier to write than machine language, and an assembler itself is not too difficult to write in machine language. Once we've got an assembler, that means we can now compile programs that are written in assembly. So that means we can write our first C compiler that takes in C, it produces assembly, but it's also written in assembly. This compiler probably won't be very it won't produce very fast code, it won't do very much analysis. The main job is simply to get a C compiler so that we can build something else higher level. What we can then do is use C to write a C compiler, and now because we've got something higher level, we can do a lot more optimizations. We still produce assembly, but we can write this thing in C rather than having to write it in assembly. And once you've got a C compiler, you can start thinking about, well, I could build a C++ compiler. Typically these two at the bottom are the only things that are actually needed on a new processor, because then you can bootstrap up to things like G++ or Clang. You may not even need to write the first C compiler. It's often enough to just do a portable enough assembler. But this is the chain of how all these compilers come into existence. So if you think about what would have to happen if you were sort of writing a compiler from scratch or compiling a compiler from scratch, the step that we usually don't do is compiling the compiler. We're used to the idea that this thing exists that takes in the implementation language we want to use. It is a compiler that's currently in machine language. It's already been converted to machine language, and it produces machine language. So we assume this has already been done, and what we end up with is a compiler. This is a thing that can be run. Based on that, we then do, this is usually where we start, we write a program in some source language, for example C, C++, Java. We compile it in the compiler that's already been created, and remember the output of one language processor can be the language processor for the next stage, and it's this pre-built compiler that takes our current source code and turns it into machine code. Once we've got that, we can do what we actually want to do, which is to run the program that we wrote. So we wrote it in our source language such as C or C++. We've ended up with a program in machine language that corresponds to it, and now we can actually put actual data in and get actual data out, which is actually what we wanted to do. So we're going to look at compilers and language processors in more detail, but it's worth getting some sense of how compilers actually fit together. And broadly speaking, there's two parts to compilers. There's a front end, which is mainly responsible for taking source code handling grammar and various types of syntactic stuff and building some kind of representation of that program. So that's the front end, going from C, C++ or Java to some kind of internal data structure that represents that program. Once you've got an internal representation, it's the job of the back end to actually take that sort of analyzed, structured program and convert it into the low-level instructions that will actually get executed. So you can see the front end is kind of taking characters and building them up into structured data, and then the back end is taking structured data representing the code and turning it into low-level instructions. We now have, in the sort of modern world, we have quite a few interprety, compilery things which are sort of neither. So chaining of languages has become very common. So what often happens is, while your compiler still lowers the language, often it will do something like taking Python and running it through an implementation that's written in C and producing bytecode. Rather than producing something like assembly, it produces a language that's actually intermediate. And we can have multiple implementations of a Python processor. So for example, PyPy is a Python compiler that takes Python and produces object code or machine code. There's also other things like Cython, which takes a high-level language like Python and produces another high-level language like C. This, in order to be run, has to be passed on to another C compiler, but we already have a lot of those and they're very good. So in terms of looking at these different language processor implementations, generally speaking, the non-negotiable thing is that the compiler has to be correct. Given correct input, it should correctly parse it, analyze it, and produce correct outputs. Generally speaking, we want the input language to be well defined. So we would like to not implement a subset of the language. So if we say that we're doing C, we should do C. We shouldn't do everything except for while loops. But also at the same time, we want to try and avoid extending the language too much, because if there's too many extensions in a language, then code that's written for my superset of the language won't compile on other people's compilers. Subject to correctness of the outputs, a second aspect is, well, how good is the generated code? How optimal is the output? So in the case of an executable produced by a compiler, we want to know, is it a fast executable? And some compilers produce much faster code than others. In the case of something like zip or unzip, then we'd worry about the quality of the output. So how small can zip make things? It always speaks the same output language, but sometimes you can make things much smaller than in other cases. Another interesting one is actually the speed of the language processor itself. So again, taking the example of a web browser as a language processor, a natural question is, well, how long does it take to receive the stream of bytes from a server, parse those bytes into HTML and CSS, and then actually turn it into the output language, which is the pixels that I can see on the screen? Subject to correctness and sort of the quality. Oh, I'm sort of messing things up here. Speed of the compiler can be relaxed. It might not be the most important thing, but you always want correctness, or you want to try for correctness. Another sort of secondary thing is user friendliness. So doing good compiler output messages is important for a production compiler, for pointing people towards exactly where things failed. Was it a syntactic error? Was it a semantic error? On what character does it occur? If you've redefined a symbol, where was the first definition? All of these difficult things to do with compiler error messages.